All right. I trust you all had a nice, scrumptious lunchtime. I certainly did myself. And for those of you again that are joining us on YouTube, welcome to the party. And I hope you all enjoy your stay while you are here for sure. Um, I expect we're going to have a couple of audit students again that jump in and um, and participate later on this afternoon. So we will welcome them when they join the party here. Okay. There you go. I hope it. I hope they get the power restored there pretty quickly, Kevin. All right, where we left off was when we first started getting into the IP version 6 addressing scheme. Now, here's what's going on with this, and for me personally, it can't come quickly enough. Currently, we are using IP version 4, the 32-bit binary address. Well, remember I told you guys that was first implemented when computer systems themselves were using 32-bit processors, 32-bit data path, and the IETF and the ICANN and IANA and all those folks decided that the 32 binary bit would be plenty enough addresses in order to accommodate every IP address requirement on the planet, both private and public. But again, they sort of missed the boat and did not consider that multiple computer systems would be existing in many households. That they didn't really take into consideration the need for an IP address for smart devices, smart TVs, smart security systems. They didn't anticipate the Internet of things, nor did they anticipate the mobile phone and people utilizing that mobile phone for as much internet browsing that they do on those individual personally owned appliances. So we literally, as I was saying, began to run out of available IP addresses because in that 32-bit binary scheme, there's only about 340 billion available addresses total there. Well, so the IETF and IANA and ICANN, those organizations, they said, well, we need to go ahead and start looking at the second version, the Internet 2, as it's being called oftentimes. And some of the manufacturers of the products, the routers, the gateway appliances, the switching devices, and so on, they figured they would go ahead and get ahead of the game and go ahead and jump in and create their switching and routing appliances where they could switch or route 64-bit addresses, because the 64-bit computer systems were just on the horizon there and they started being manufactured. Well, IETF says, nah, we're going to get ahead of the game. We're going to define IP version 6 at 128-bit binary address, which actually is somewhere in the neighborhood of it's a mathematical version of a term that I've never heard before. It's called undecillion. Excuse me, it accommodates 300 undecillion addresses. And that's actually 300 trillion available addresses in that 64-bit scheme. That's more addresses than we'll ever be able to use up on this and a couple of more complete planets forever. So they did a good thing there. And me personally, they can't get there fast enough. It's very cut and dry the way the address is set up. The first 64 bits is the network address. The last 64 bits is the interface ID, the system address, the host address, as it were. And that also embedded in there in part of that last 64 bits is the MAC address of the network adapter that we talked about earlier, the 48-bit address there. There's a couple of things that are changed radically. The whole subnet masking, class-based private address, public address concept just goes away. It's just not required anymore. We have enough addresses there, and if they're set up properly, you have just a nearly unlimited number of addresses available that you can accommodate any public, private, or worldwide network in essence. And the way that the network portion of the address is laid out is conceptually very similar to the way that our telephone numbers are, worldwide digital telephone numbers now. A lot of folks don't realize, they think our phone numbers are just a 10-digit number. It's actually a 13-digit code. And under the covers there is a 3-digit country code. Then you have your 3-digit area code, your 3-digit exchange code, and then your 4-digit actual phone number within that exchange, within that area code. The network address is very similar to that in that it has a header or a first several of the bits of the network ID. Conceptually, same thing, a country type of code, country regional type of code layout. It has sort of a like a country, a region, a state, that kind of concept. But it's the country, the region, the internet service provider, network provider, that kind of thing. And then inside of that, the last 64 bits identifies each individual network adapter within that network ID. So broad ranging addressing, whole subnet mask concept out the window. No difference between public and private addressing per se. There are a whole host of reserved types of network addresses that reserve some of the addresses out on the public internet for things like worldwide documentation, testing areas, codes that are reserved for testing certain types of network configurations. There'll be certain network IDs there that are isolated for governments and militaries and things like that. There are lots of organizations now that have already begun to prep for and to integrate some of the IPv6 addressing inside of their autonomous networks. And then there are a couple of host server type host machines that have been set up now that are giving the networks the ability of doing this, what they call dual stack processing, where a host machine has both an IP version 4 and an IP version 6 address. I mentioned to you guys earlier the IP configuration command. If you run an IP config command on your computer right now, it will show you what your assigned IP version 4 address is, as well as to give you a proposed or a preferred IP version 6 address. So you can see it now. There are equivalents to everything that we looked at before. The link local addressing I was talking about, the PIPA addresses, there's a version of that. Those all begin with FE80. And the way that the 64-bit or 128-bit binary address is set up, you don't look at it in decimal format anymore. It's hexadecimal. Very similar to what we looked at with the MAC address, only longer. So a little bit different concept. There's a bit of a learning curve there. And it's going to come down to the worldwide community finally telling the rest of the worldwide community, as of this date certain, we're switching over to IPv6. And if you don't have your systems upgraded to where they can route and switch a 64-bit address or a 128-bit address, then you won't be able to communicate on the World Wide Web anymore. And the main holdback, one of the main holdbacks anyway, as far as making that transition, is that I was telling you guys earlier, a lot of the equipment manufacturers, the routers, the switches, the gateway appliances, and so on, they thought they were jumping ahead and manufacturing their devices so that they could route, switch, and move 64-bit packets of data. Because, like I say, the 64-bit computers were right on the cusp of starting to become more commonplace. But then the IETF sort of leapfrogged right over that 128-bit. So there are literally still to this day tens of thousands and maybe even hundreds of thousands of switches and routers that are deployed out all over the World Wide Web still that are physically incapable of moving a 128-bit address. So there's going to be some time frame there and some lag before those network owners finally upgrade their equipment. But I think it's going to be very similar to the way it was put forth when we finally made the switch from analog TV broadcast to digital TV broadcast. And I always make fun of all my redneck relatives down in the southeast United States, when they finally made that switch over, I could hear the collective groan from all of my relatives because they couldn't receive their three channels over the antenna anymore. But I think it's going to finally come down to the network community worldwide is going to have to. Here is the stake in the sand. If you don't have your equipment updated by that point, you won't be able to communicate over the World Wide Web anymore. So now that will sort of shake and rattle them and hopefully motivate them to go ahead and upgrade all the equipment that can't exist in that IPv6 world anymore. There are some configurations now that allow us to do the 4 to 6, the 6 to 4 translation, but mostly inside of an autonomous network, not out over the public internet. Okay. This is the first of the labs here that I'm going to assign you guys. This lab exercise here as part of your homework tonight. That's really cool. You go in and actually log into a management console, and it shows you how to set up a router, how to configure your own router there. That's something every A+ technician and network engineer has to know how to do. Okay. So I will be assigning that lab as part of your homework later on tonight, and you'll get some quiz questions about that as well. Now, I mentioned several times already the common ports and protocols. I gave you guys the link to that document where you could download that off of the wormhole site I set up for you guys last night. Now, there are very common communication software protocols that we use and the ports that they actually operate over. And then we use those every day. You're logging into a website. You're using either port 80 or port 443, HTTP or HTTPS. When you're doing video protocols back and forth, you're using ports 5060 or 5061. There's a protocol there called session initialization protocol. And it's the same thing we use for video transfers, for voice over IP telephone calls, things like that. Email protocols. There are three major email protocols: the Internet Message Access Protocol, the Post Office Protocol, and the Simple Mail Transport Protocol. So all of these software protocols and the communication ports they communicate over, you have to know these. The management responsibility for most of these, the setting up the communication port, outbound, inbound port, and assigning the application protocols to those network connections, is typically the responsibility of the transport layer in your network session area. Now, in the TCP/IP model, the transport layer has been sort of incorporated in part of the application and part of the network layer. There in the old 7-layer OSI network model, it's a standalone layer, the fourth layer in the network stack there, but it's been sort of incorporated into the newest version. There's another view of the Wireshark capture utility that I gave you guys the link to. And here it's actually showing you a string of data frames and packets that are communicating with an interactive TCP type connection. If you look at it here, it actually begins at this area right here. The first thing that happens in a TCP network connection is a synchronization request. This guy right here is sent to a target system. In this case, they're trying to establish a web server link. So they send that synchronization request to port 80 on that target system. Now, if indeed that target system is ready to make a connection, it will send back, and you see it in the second area right here, a synchronization acknowledgement. Yeah, I'm at port 80. I'm ready for a connection if you want to. Well, then the source system will then send back the third. It's the bind, we call it, but it's an acknowledgement. All right, well, let's talk. So it sends that acknowledgement flag back, and it says, all right, let's have a communication session. Well, then in this case, the browser has now connected to a web server, a website on port 80, which is a non-secure website, HTTP protocol. And then going forward from that, you'll just see a whole collection of the acknowledgments. And if we were able to scroll this down, you'd see a whole bunch of those until the session was reset or finished. So that is a TCP based connection, real-time connection. There's a handshake, there is synchronization, there's timing, and I can track those whole every interchange of that using a tool like Wireshark and see the entire interconnection and the exchange of all the, in this case, the HTTP headers that travel back and forth between the web browser and the web server. Here, Wireshark also highlights the source IP address and the target IP address, and it shows in both directions there. Okay. So all that information is clearly visible by capturing those data packets with a tool such as a Wireshark. Now, there's another tool, it's a command line tool that's used on Linux system. It's called TCP dump. Allows me to do the same sort of thing. Wireshark is got this clever looking graphic user interface that runs under Windows type of environments there, but it shows me the whole interaction there. Now, a transmission control protocol is, like I say, a time synchronized protocol that establishes that initial connection. It does the synchronization and the acknowledgement, and then the acknowledgement of the data frames that flowing back and forth between. It not only guarantees the integrity of the data because it does error checking on each individual data frame, but it guarantees the delivery of the data packets. So if I am in a TCP type of session and a data pack frame is dropped off the network because it timed out or it's damaged or whatever, well, the target system will continue to send back a request. Okay, you need to resend me sequence number 145. I hadn't received it. And it'll keep doing that until it completes the delivery of the data. Okay. So interactive, timed, synchronized. Now, on the other side of the data frames is this concept called UDP, User Datagram Protocol. It's often referred to as best effort. For instance, this video and audio broadcast we're doing right now is a UDP type of communication protocol. Doesn't guarantee that every frame that I'm transmitting is going to be received on your end. If a frame is dropped, oh well, it's dropped. Your connection doesn't request I resend it. Okay. The UDP datagram there's less information in each header packet. The data frames themselves are very set sized and so on. And then there's about half of the communication protocols that we use on a daily basis that will do either or the TCP or the user datagram protocol. And they just make the decision typically at communication time because it evaluates different metrics. Again, network bandwidth, bottlenecks, dropped data frames and packets, things like that. Now, there are certain of the communication protocols that only operate as TCP time synchronized. There are certain of those that only operate as UDP, user datagram, best effort. And then again, there you'll see a couple of these that are either or. Okay? Well, I guess all of these. Yeah, there's a network BIOS protocol, net BIOS transport. That is one that's either or. It will make the decision, and the others here are just they're all one or the other there. Memorize this chart here in preparation for your certification exam. Okay. There's your domain name services. It's communication port there. And these are all non-secure communication protocols and ports here. DNS actively listens on port 53. DHCP, server listens on 67, client listens on 68. It's a back and forth type of thing. And so there's the communication ports that are used by these different protocols. This is your simple network management protocol, lightweight directory access protocol. There's secure shell, old trusty telnet. That's the very first communication protocol that I ever used when I was working on the computer's merit badge a gazillion years ago was telnet. And it gives you a command line interface to a target system somewhere, but it's not secure. We implement a secure connection by using secure shell, and then I run the telnet or the FTP commands either over that secure shell connect. Here's one of the protocols that falls outside of that normal 1 to 1024 common ports range. This is remote desktop protocol, port 3389. That's where I can log into a target system and take control of it for doing support there. If you don't understand what these acronyms are, look them up. File transfer, Hypertext Transport Protocol, non-secure. Hypertext Transport Protocol, secure. There's server message block. That allows me to share files across different operating systems, one of the main things that one does. And here are your three major email protocols. Simple Mail Transport Protocol, Post Office Protocol version 3, and Internet Message Access Protocol. The latest version of this is version 4 or 5, IMAP 5, IMAP 4, and the ports that they communicate over. You must know these ports and protocols. You must know if they are UDP only or TCP, okay, or if they are one or the other. Those are the things you have to study up on to prep for your exam. Highly recommend that you create flashcards to study this stuff, and create your own flashcards, by the way. In my opinion, one of the best ways to actually prep for these kind of things. Okay. So look all this stuff up, write it down, study it again and again and again. You will get questions about those communication ports and protocols and what they do. Okay. So brush up on that stuff. Now, networking, I told you guys before, as A+ technicians, you are going to find yourself being charged and maybe even totally responsible for some network configuration, network troubleshooting, those kind of things. So there's several different types of networks and several different types of physical and logical setups that I need to perform on those. Now, one of the things that I told you about earlier, I'm a big fan of allowing DHCP to manage all of my IP addresses basically dynamically. However, there are certain computer systems inside any small, medium to large size network, especially, but even in small SOHO type networks, there are certain systems, host machines inside there that I want to make certain always have the same IP address. Think about your gateway device or your DNS server or your DHCP server or your firewall or the web server. Certain devices in my network, I want to make certain always have the same IP address. I don't want to be charged with going to each of those individually and manually configuring those. I can use a function inside of DHCP. It's called IP reservation. I go into the DHCP server and I configure it there. First, I have to get the MAC addresses of all of those individual systems. Okay. So I get the MAC address of my gateway router box. And in DHCP, I say, well, every time this particular MAC address starts to log on, I always want you to give it this IP address. So you key it there. You don't have to put in subnet masking or any of that stuff. DHCP server it's configured one time and all of it knows everything after that. Okay. So every time that system logs in, it always gets the same IP address. And it kills a couple, as my dear old grandfather would say, it kills a couple of birds with the same rock. It not only assigns that same IP address to those systems, but it removes that IP address from the pool of available IP addresses that I assign dynamically to other systems, thus eliminating the possibility of me assigning the same IP address to two different systems. Okay? And the DHCP server handles all of that. I only configure it the one time, and it really cuts down on the manual management requirements that I have to go through for DHCP. Now, the whole DHCP protocol and the whole process is dependent upon what we refer to as DORA, D-O-R-A. When you first start to log into a session, the very first thing your computer does is looks for the closest DHCP server. That's the discovery phase. Okay? When it finds the DHCP server, it presents the MAC address, your MAC address, to the DHCP server, offers that up. Then it says, I need an IP address. Okay. DHCP server takes the next IP address on the bottom of its available pool and says, would you like this IP address? And then I say, yes, I would. So I acknowledge that. It updates the DHCP server now with the IP address that it assigned to my MAC address. And don't forget that ARP cache, the address resolution protocol, it also updates that, because I'm getting a new IP address, probably not the same one I used on my last session, but it now updates that ARP cache so that it associates the IP address I just got assigned to my stable, never changing MAC address. Okay. And that's the whole DHCP protocol concept. It happens every time when I attempt to log in and get a new session started in a network. And I really like that DHCP IP reservation too, because it automates a whole bunch of the functionality. Now, way back when the internet first came about, they had these, they call these top level domains. And originally there were a handful, primarily there were three. There was .com, .net, and .org. And then out of that grew, I mean, you got a dot everything you could imagine. Each country has their own high-level domain, .uk, .ca, .ru, .jp. They have .mil, .gov, and the dots continue on and on and on. Those are all what they call top-level domains. I have my own personal website server. My domain name for my website is DonnieHelms.com. But then downline from that, we can also define what's referred to as subdomains. For instance, in a company, you may have sales.company.com. In my server world, I have store.donniehelms.com. I've got wiki.donniehelms.com. I've got guest.donniehelms.com. Now, they're all covered under my same domain registration. They're not active as of yet because I haven't filled out the information for them. But once I have all of those areas ready to launch, then those will be the subdomains that are active there as well. So it's a very hierarchical setup environment. You have your root servers, which have the, that contains the overall internet domain information, and then the top level domains and any subdomains down from that, country domains, things like that. Now, once you register a domain name with whoever your registration host might happen to be, then that information is then distributed out to all of these web-based regional DNS servers all across the World Wide Web. And many organizations, actually most organizations, medium, large-size organizations especially, will maintain also internally these large regional DNS server machines as well. Anytime I fire up my web browser, we key in a name, a web name. Like when you guys, I would bet $1 to a donut that most of you had never visited DonnieHelms.com before yesterday. Okay. So when you keyed that in, the first thing that occurred was it looked in your web browser cache to see if it could find the IP address that was associated with my website. Probably didn't find it there. So then it goes outside and looks at whatever your most local DNS server might happen to be. That may very well have been at your internet service provider. If you're inside of a private company, it may have looked at your internal DNS server first. Somewhere along the way, it would have found, probably at your regional or your ISP, it would found the IP address that was associated with my website. And then it backtracks all the way back to your browser and updates everything along the way. So now, if you go to DonnieHelms.com again today, it probably doesn't have to look any further than your browser cache. Your system, each individual host machine, maintains a file, and the file is named hosts, HOSTS, and it lives associated with your system, and it has all of the known IP addresses for all of the computers or systems that you have visited or communicated with. Okay? So that's the DNS query concept, and it translates the fully qualified domain name that we key in on our browser or on our applications, and it associates the IP address with that because we communicate with the IP addresses out over the public internet. Now, inside of these DNS servers, whether it's local, regional, or an internet-based DNS server, there's about, I don't know, 6, 7, 8 different types of data records that exist inside the DNS database. There's an A record that identifies domains with an IP version 4 address. There's a quad A record, a 4A record that identifies any domains that have an IP version 6 address. There's pointer records, PTR records they call it. So if I know an IP address, but I don't know the fully qualified domain name, it does a reverse lookup on those PTR. There's a mail exchange records for mail servers, and identifies all the characteristics, attributes, and properties of the mail servers. There's server type records, SRV records, that identify different services that are spread out through networks. There's text records, TXT type records, that is just further information about attributes and properties of web servers. There are records that identify the policies and procedures that dictate how email is sent to target email addresses. SPF records, called those Sender Policy Framework. You have records that in there called DKIM and DMARC records that identify digital signatures, and any cryptographic algorithms are utilized for encrypting of email, primarily mail sources, and sending and receiving encrypted emails. The DMARC information is that is your domain-based message authentication, reporting, and conformance. It sort of is there to sort of enforce or prop up the sender policy requirements and your domain key identification information. So it's sort of an addendum to those types of records. And all these things exist as data records and different data record types inside the DNS database engine. And all of that is used to define the IP address, the fully qualified domain name, and all the attributes and property definitions for each and every system that is out over the full World Wide Web. Now, I told you guys briefly earlier about the virtual local area networks. Inside of these new managed multi-layer switches, it gives me the ability to, within my local area network, if I've got 20 people in my company total, I can wire them all into a singular switch device, because you can get these things up 48 ports on an individual device. But then I can further isolate them in their own virtual local area network by getting into the command language, the configuration panel on the switch. And as I was saying earlier, set up VLAN 10 and VLAN 20 and VLAN 30. So I can isolate everybody in the HR department in VLAN 10. I can isolate everybody in accounting in VLAN 20. And even though they are physically connected to the same physical switch, that virtual local area definition gives me that isolation, because somebody in VLAN 10, they can't communicate directly with somebody that's assigned to VLAN 20. That traffic has to be routed through a gateway device, okay? So it gives me that extra layer of isolation and security wrapper, even though they are physically isolated or physically connected on the same piece of equipment. It really gives me sort of a twofer there. I cut way down on the number of required pieces of equipment, but I also give me that centrally managed, if you will, configuration there that allows me to further isolate users inside the virtual local area networks. And it's conceptually the same thing as if I take the users and put them in a completely different building, completely different room. It gives me that level of network division and segmentation there. Now, VPNs is a concept that everybody, in my opinion, should be using. virtual private network is sort of a secured pathway, as it were, through the internet, which is the most unsecure environment you could ever imagine. Okay. And look at it like this. Let's say I am, like we all are now, working from a home or an office location. In order for us to connect to the servers that we're talking to, we fire up our browser and we go over some type of internet connection. Now, I want you to imagine, if you will, that the internet, which is between you, your client at your home, your browser at your home location, and whatever server you're logging into, the internet is this big old granite wall between you and whatever server you're logging into. Same thing for remote workers logging into the company they work for. Well, when I fire up my virtual private network client, consider this. It's like taking a little tiny 5-micron diamond headed drill and drilling a hole through that granite wall, which is the internet. And I've got all that granite surrounding there. Nobody can get to my connection, right? They call it tunneling protocols, which virtual private network clients actually implement. But they also then wrap another layer of protection using encryption algorithms around that VPN connection there as well. So it is literally like having 3 wrappers of protection around my connection between my host machine and whatever server machine I happen to be talking to. There's 2 different implementations of VPN. It's called a client to site, where each individual client computer system runs some kind of virtual private network client program. And then there's a version of it. It's like if you have a home office, branch office, it's called a site to site VPN. Either way, when I communicate through the public internet, I'm actually attaching to, on the target side, a virtual private network gateway appliance, which is very secure, uses these same tunneling concepts and encryption algorithms. So just no better way to actually communicate remotely over a public, very untrusted, unsecure kind of network. See? So in the site-to-site version, you have a VPN gateway sitting on either end. And when those systems are booted up, they go ahead and pre-drill multiple VPN tunnels between the 2 locations. And individual users don't have to, they just push data down the pipe, basically. And it's VPN gateway to VPN gateway connectivity between the multiple locations there. So very, very secure environment, the most secure that you can get to date anyway. I run a couple of VPN clients here locally. Well, I've got VPN on my phone, my tablet, my laptop. All my systems are very, very tightly secured with the VPNs. All right, everyone, if you would, I would like for you to navigate over here to your practice panel here. Now I'm going to have you guys do your lesson 5 quiz. There are 10 questions total there. And then I do want everybody to go back and repeat the lesson 4 quiz. Now, those of you that are dialed in on YouTube, you won't be able to participate in this, but just hang with us because we're going to be back at it here shortly. So go over lesson 5 quiz. I want you to post those scores. Then I want you guys to go back and repeat lesson 4 quiz. Okay. And you will see, you'll boost that score up. 20 questions total there. Now, I'm going to set your timer for 30 minutes on this. I do not believe it will take you guys that long to do both of these. Okay. But do both of those quizzes and post the scores. And when I see everybody's scores show up there, we'll have time left, but I'll go ahead and shut that time down. And we'll dive on into our next lesson lecture here. Or, I was looking, we may do another PBQ right quick, but we'll see. You guys go ahead and jump on that lesson quiz, those quizzes. Again, I'm going to set your timer up for 30 minutes. I do not believe it will take you that long. But when you get through with these both, post the scores. And when I see all 3 sets or all 4 sets of scores there, we'll come on back in and start and get into the next lesson here. One more lesson I definitely want to finish before the day's up. Okay. All right, go for it. Good luck, and I'm looking forward to seeing those scores. All right, looks like just about everybody. Michael, if you're still working on that, carry on, sir. You'll be finished with it in just a second, I know. I'm going to go ahead and halt the timer now and get ready to get on into our next lesson here. Well done, everyone. And once again, you guys proving me right all over again. You know, the second, third time you do these lesson quizzes, then it's embedded, then you know it. Okay. So very well done there. Very well done, everybody. All good news. All right, let's dig on into this next lesson here and see what we can see. Now, this sort of carries on and furthers some of the information we looked at previously in the previous lesson, specifically towards defining more details about some of the network services that you guys will indeed be supporting here. Okay. Yeah, you did pretty pretty okay there, Kevin. No doubt, buddy. I'm glad you're back online with us there. Excellent. So let's take a peek at some of the network services here. Like I say, we touched on some of these already. Now, services that are typically provided up by your individual server host machines that are spread out through your network. I talked about the network basic, your basic I/O BIOS type of functionality. NBT is the way that this protocol is actually listed. And it's your basic input output functionality. Net BIOS is what we call it. That operates on ports 137, 138, and 139. And I tell you, one thing that it supplies is the support for older Windows systems specifically. Older meaning prior to Windows 2000, legacy versions of Windows. Server message block is a means of being able to share files across different operating systems. Primarily was put in place to begin with to provide the capability of sharing files from a Windows environment to a Mac OS and Unix and Linux environments. Operates on port 445. These are all unsecured ports, by the way. All of these protocols have a secure socket counterpart where you can set these things up in an encrypted and a secure mode as well. These are just the non-secure versions of them. FTP, File Transfer Protocol. File Transfer 21 is the primary control connection to an FTP server. And then port 20 is utilized for actually moving files from an FTP server to an FTP client. And once again, the raw version of that is not secure. If I wanted to do a secure FTP, I would establish there's a secure FTP using Secure Shell. There's also a version of FTP that I can implement using a digital certificate, much the same. I would create a digital certificate with a public key, private key for a web server. Same concept. And then use the encryption algorithms and some of the tunneling protocols and so on. That's these guys down here. There's your secure FTP for secure shell, and then FTPS, FTP secure using your digital certificate, transport layer security functionality there. So those are network protocols, file services kind of protocols, and sharing protocols that you need to be aware of. Now, the web servers, I told you, your client is your web browser. Okay. We fire up a web connect. If you're doing a non-secure website, it is port 80, the HTTP protocol. If you are doing a secure website, then it's HTTPS port 443 is the communication port there. And the secure web server also utilizes digital certificates. I get a digital certificate from an entity known as a certificate authority. The certificate it uses certain encryption protocols. It creates a public key and a private key. And the whole connection between your client and a secure website is secure. It's an encrypted end-to-end encryption function. And now the latest versions of the digital certificates, excuse me, in addition to using what we call a secure socket port 443, it also now incorporates what we refer to as transport layer security, with additional very strong encryption algorithms and the support for these tunneling protocols that I mentioned earlier. You go to a certificate authority, you purchase the digital certificate, you download it, you install it on your web server. And here's the way the whole process works. When you guys visited my website is protected with a digital certificate. You, in your browser, you type DonnieHelms.com. Boom. Your browser sends a request to my web server. And the first thing that occurs is my web server sends down to your browser a copy of my digital certificate that contains the public key. Now, remember, in a digital certificate, there are two keys, public key and a private key. Private key remains up on my web server. It's not distributed out to the public at large. So when your browser receives that copy of my digital certificate and the public key, it does a couple of things. It has to then validate and verify that the digital certificate that my web server sent down to your browser is still in good standing. So it finds that information out on the internet somewhere. And then three very quick things, important things, however, occur. And it happens so rapidly, you just don't see it. It's just the blink of an eye. Your URL, the web address up top, changes to https://DonnieHelms.com. And your padlock icon that's in your browser shows locked. And most of the new browsers, the web address line itself turns green. And those three things, like I say, blink of an eye, and it tells you your browser, yep, this is a secure connection. And then we start exchanging data between the site. Okay. And all that stuff occurs before the page actually is displayed into your web browser. But again, very rapid. You don't actually see it occur. And it's operating over the secure socket. We call it port 443. And it has differing layers or different levels of transport layer security that is implemented with these tunneling protocols. So it is literally like three wrappers connect or surrounding your connection there. Well done, Michael. Well done, sir. Very good. And now mail servers, same thing. Mail services have a non-secure environment as well as a secure environment. There's three major protocols. There's Simple Mail Transport Protocol. That is the software protocol that is required to move mail from email server to email server. And then there's two other protocols that are utilized to take the email from the email server and pull it down to your client machine. Those are the other two email protocols primarily. There's a Internet Message Access Protocol, or POP protocol, the Post Office Protocol. SMTP, by default, the non-secure version, operates on port 25, but there is a secure submission of the Simple Mail Transport Protocol that operates on port 587. You have to remember these ports because they will ask you questions about them. Okay. So this is what I was telling you guys earlier. I would strongly recommend making you some flashcards so you can memorize this stuff. Here's the two delivery mail protocols. Post Office Protocol version 3 is the latest version of that. Primarily, the non-secure version operates on port 110, but you can set it up as a secure protocol using port 995. And a lot of your email service providers, by the way, are now requiring that you set up the secure connection rather than the non-secure. The IMAP, the Internet Message Access Protocol, operates on port 143 by default, but you also can set it up in the secure socket using port 993. And again, most of your email providers are requiring this secure setup. Now, the major difference between POP3 and IMAP is that in the post office protocol, It pulls the messages off of the email server, and you manage them locally on your system using whatever email client you happen to be using. In the IMAP, it allows you to manage the mail folders that are on the server, as well as pull the information down to your client machine, whatever email client you happen to be running. When you set the email services up, there's three basic bits of information that you have to supply for the connectivity. You have to know the name or the address of the SMTP server that you're pulling mail from. You have to provide, of course, your user ID and your password. And then you have to give it the inbound and the outbound addresses for your email services. And most all of your systems will provide that automated setup for you. Where you might run into having to define it is if you configure your mobile phone or your tablet device to receive the email, then you may need to know that information. But your email service provider will give you instructions as well as the information you need to key in on your incoming and your outgoing mail server name. Okay. So, and again, lots of them are requiring that you use the encrypted email, the secure email, rather than the plain Jane non-secure. Here is your directory services, the LDAP services, Lightweight Directory Access Protocol. The non-secure version of that operates off of port number 389. And that is managing your what they call the subjects and the objects inside your network directory services. Now in Windows, we call that ADS, Active Directory Services. In all of your other operating system environments, they simply call it LDAP, Lightweight Directory Access Protocol. I have a LDAP database that is set up, and inside that database, it contains two different entities that are referred to as the subjects or the objects. The subjects are individual users' profiles, group profiles, system service profiles, and then the objects are, well, the network itself, the individual systems and subsystems inside the network, the host machines, the files, the directories, the folders, the databases, everything. So you use the directory services to assign access and permissions to a subject to gain access to the objects, including the network itself. Inside of most of your directory services, they have a function in there. It's referred to oftentimes as a AAA compliant server. And those three A's are authentication, authorization, and accounting functions. In the Windows environment, the default, not Windows, but your wireless environment, your wireless access point manufacturers, their default AAA compliant servers there is called Radius. And that's an acronym, of course, like you guys didn't already have enough acronyms to worry about, right? Radius is Remote Authentication Dial-In User Service, Radius. And in the Windows environment, the AAA compliant service there is referred to as Kerberos with a K, Kerberos. And that's sort of the gatekeeper application that provides you the ability to log into the network, to go to the directory services and have all your permissions and access assigned based upon your profile and whatever access and permissions are allowed inside your network. Okay. And that typically is set up by some network administrator or security administrator, something like that. Okay. But LDAP is what that's the protocol and the database engine that actually houses and manages all of that information. There's also a secure version of LDAP, LDAP Secure they call it. It operates over port 636. The prime version of it, the non-secure version, is port 389. Okay. You should, and you'll get a lot of pushback, unfortunately, from network administrators. I always try my best to require all of these network protocols to use the secure versions rather than the non-secure versions. And the network admins, they'll push back, oh, it's too much overhead, too much latency, too much doesn't impress me anymore. Is I can get additional security out of that, then yeah, we'll go. But plus the fact that technology has taken care of that lag time, that latency, that slowdown that was caused in the past by using encryption. It's not noticeable anymore. There's old trusty Secure Shell. Now, Secure Shell is not a native Windows protocol. It's been around forever in Unix and Linux environments, but we have to use a particular program, a client program, if I'm going to use it for like secure telnet or secure FTP in a Windows environment. The client is this is a copy of the client PuTTY that I use here on my system, but it's just a client application that fires up the secure shell connection, and it operates over the secure socket port number 22. And then I can use secure shell like telnet commands or secure FTP commands over that end-to-end encrypted connection there. Telnet, like I told you guys earlier, that's the very first command and protocol I ever used when I first started working on my computer's merit badge, and that was back in the fall of 1967. So, yep, I'm older than dirt. Um, then we have remote desktop protocol. That's the one I was telling you, sort of outside the normal common ports range, port 3389. It gives me the ability to log into a remote system, take control of it, and to manipulate the machine, do remote support, that kind of thing. I also I've used a tool, still use it quite a bit along these same lines. It's a secure connection. It's called a Team Viewer. You guys may have heard of and used that before. Same concept as a remote desktop protocol. It allows me to attach to and take control of a target system, log into it just as if it's on my desktop in my system here. I support my brother on that quite a bit out in the Mesa, Arizona area. He is, shall we say, not technically apt. So he'll call me up every now and then and ask me to fix what he unfixed. And plus, I get to, not only do I get to fix his computer issues, I get to communicate with him because I hardly ever get to see him anymore. He don't travel this way, and I very seldom am capable of traveling that way, just working too much. But I'll get back out and hug his neck here for too long. This is your simple network management protocol. That allows me to manage events that occur on individual host machines that are spread out in my network. The SNMP operates on ports 161 and 162. It allows me to sort of gather status information from SNMP agents, they call it, that live out on individual host machines. And, basically status update information about a client, if it's working properly and so on. I can set up the agents out there in the field to periodically, it does a process called walking their status up to what's referred to as a trap area. And then the SNMP server then wakes up periodically and pulls that information up for analysis. This OpenSense client here, that's an application program that sort of allows me to do some SNMP kind of management, system log kind of gathering information and management. And it's an open source piece of software too. I'm a big fan on the open source stuff. Your system log type of environments, and that's more along the lines of Unix, Linux, Mac OS, Android. They all use a very constant and consistent logging process. Client machines out in the field push log information up to a server log, and it uses ports 514 to push those log messages up to the different logs there. SNMP is pretty much what we use in a Windows type of environment. But the syslog is pretty much all the other operating systems in the way that it logs information there. So those are individual network hosts that we see, and your primary use stuff, file and print services, email services, web servers. We talked about the HTTP protocols, the simple network management protocol, the email services, your directory, your LDAP services. All of those are pretty common network protocols that we see utilized in every network every day, all day. Okay. Now, this is a lab that I'm going to want you guys to take a look at. It's not really going to answer a whole bunch of questions that you might get on the exam, but it does show you the capabilities and some of the tools that we utilize in order to analyze network traffic. And it will allow you to start making sense of some of the messages that are captured and sent up line by the different network protocols and so on. Okay. Not, like I say, not going to answer a whole bunch of questions on your exam, but it is something that as an A+ technician, especially an A+ technician is maybe responsible for networking tasks as well. That would certainly be a good exercise for you guys to go through there, no doubt. Okay. So probably going to assign that as one of your labs. I mean, one of your homework labs too. Now, I've talked quite a bit about these Internet of Things, these, the home automation systems, the Internet of Things, the voice things like that. There are certain devices and appliances that we see out that are spread out in the network that perform very specific kind of functions. Proxy servers are services that basically act on behalf of or as a proxy for either incoming traffic or outbound traffic. Proxy server can automatically intercept requests coming from outside client machines trying to get into the network. They can run those through, again, the access control list, much like a firewall that we talked about earlier. And I can have proxy servers that do the same thing, intercepting traffic that is being directed outside of my network. Think about a proxy that limits, certain websites that are not allowed to be visited outside of my network. And think about a proxy too that limits certain number of outside resources, the access into client machines inside my network. Again, acts much the same as a firewall. In my opinion, a firewall is a type of proxy in that it acts on behalf of some other kind of function. And I can put, extreme content filters and access control list type of entries. And I'll tell you another place that we see the proxies implemented quite a bit, as a matter of fact. Lots of organizations, small and medium-sized organizations in the past, spent just boatloads of money on setting up firewall equipment, firewalls, either software and sometimes software hardware configurations. And just because there's some new exciting firewall comes along, doesn't mean they're just going to boot the old system out, because they paid a lot of money and have a lot of time investment resources in that. So, but some of the older firewalls simply are not capable of doing what we refer to as stateful analysis, meaning they don't have built-in database engines. They can't capture data points or decision-making stuff about each packet that comes in and storing in a database. They just, it's whitelisty kind of stuff. Allow this or allow this or allow this or allow this, but deny everything else. They can't do any sophisticated analysis. So we find that lots of organizations will set up these proxies right inside the firewalls to give them that more sophisticated if then else kind of capability, or the more sophisticated filtering capabilities and tracking capabilities that the old firewalls simply don't have. Okay? So it's sort of a supportive type of control that we put in place there to assist the firewall. And now eventually, we'll roll the old technology out, put some new technology in, which may kill both of those birds with the same rock. But that's just a compensating kind of control, they call that. Okay. From a security perspective, there's a handful of different network appliances, network functions that we have. There's, of course, your firewall, proxy services. We have what's called intrusion detection or intrusion prevention systems, antivirus, anti-malware systems. We have your email gateway spam filter type of functions, like the proxies I was talking about. We can set up inbound and outbound content filters. And there's these clever little systems now that we've seen called data loss prevention or data leak prevention systems. All of those acting together give me what's referred to as defense in depth. Whereas I have multiple concentric layers of security apparatus that all act in concert to guard against the bad guys being able to break into my network and steal my stuff, right? I want the biggest, baddest, most 10-foot tall and bulletproof perimeter network security you could ever imagine. Yeah, I want a big firewall. I want antivirus, anti-malware. I want content filtering. I want a proxy services. I want everything rolled into this big bad network perimeter security. But I want that same thing rubber stamped on all the host machines inside my network as well. Remember the concept I spoke about earlier: zero trust, always verify at every step along the way. Right? Because I tell you, credentials are so easily stolen or people tricked into giving them up nowadays. And there's so many ways to gain a foothold into a network, into a singular host machine, and then use that as a landing or a starting point, and then work my way through the network in full-on penetration testing and abusing host machines all along the way. We see sort of a concerted movement now into setting up all of these security functions into what's being referred to as a unified threat management machine, UTM, where you have all these things wrapped up in one big fat server class machine that performs all those functions. The problem with that is a single point of failure possibility. And from a networking and security perspective, I want to try my best to eliminate all single points of failure in my network configuration. So for my money, I would set up, instead of one of those, I like the idea of being able to manage all that functionality in a single location, but I want at the very minimum two, and my preference would be three of those. So triple redundancy with all of those things at different entry points or exit points in my network. So I've got a fail safe, you see. So, and the hardware competition, manufacturers, software changes in the way that software is priced and licensed really plays into being able to set those things up in that redundant mode there, thus eliminating that single point of failure function there. Okay. So I'm a big fan of the UTM systems, but remember, it's a big red flag of a single point of failure possibility. One thing that I can do and we see this a lot set up on web servers, app servers, print servers, storage devices, we'll have these load balancer machines that front end those things. So it's designed to keep from overloading and overwhelming any one of the back-end server systems. And by default, all of the inbound traffic comes to a singular load balancer IP address, and then it basically round robins the handoff of the information on multiple clustered servers on the backside. And those servers have to be symmetrically linked, so any updates on one is automatically handed off to the other two or three, or however many there are. But I like the concept of load balancing. It is also a security apparatus that sort of cuts down on the possibility of denial of service attacks being successful as well. Okay, so yet another good traffic management function, but also a security apparatus there as well. One thing I really have to pay attention to, and this is especially when I start doing security assessments and vulnerability assessments in my systems. Older systems, legacy systems, are a weakness in any kind of network, no doubt about it. We have to understand first and foremost that all systems, hardware, software, and the combinations of the two, have an end of life. They have a sunset date. I need to consider that expected lifetime and that sunset date from day one when I install these things. In many cases, and I've a couple of boys that were students of mine years ago have 3 different companies up in the Northeast United States. They got them and they can do anything they want to with them because these two cats, one of them's older than me, which is old, way older than dirt, but they are the only game in town because they're old time programmers that know how to work on these antiquated systems. And there's three large companies up there that are still dependent on some of this antiquated technology. And one of them, they got hardware that they're still dependent upon as their primary business line. That this hardware hadn't been supported by the original manufacturer for 20 years. And it's running software that these two guys are the only ones that know how to work on it. So they can charge them whatever they want to when they have to go in and fix some stuff because they're the only game in town. Well, you don't want to be in that situation. You don't want to be vendor locked and at the mercy of some old crusty programmer that, one of them calls me up. This has been a couple years ago. Yeah, bud, I want to tell you, they called me up. And this old boy's from Alabama, but he lives in New Jersey now. They called me up. They got a problem with that old VSAM system up there, and said they had to have some updates on it right now. He said I told them it cost them $375 an hour. They didn't even blink an eye. So he can charge them whatever he wants to because he's the only game in town, you see, where you don't want to have that vulnerability in your particular environment. That introduces all types of risk to your organization, both from an operational and a security perspective. Now, there are these specialized type of systems that we refer to as ICS systems, industrial control systems. We see those in operational technology networks. They see it. We see it in manufacturing distribution. We see it in power generation, logistics control, communications. We have these large networks that may be spread out over a pretty vast distance rather. Think about wind farms, solar farms, hydroelectric dams. They have all these small, sometimes singular function computer components that may be spread out over miles. And they're all communicating some type of typically low-level status information upline to some centralized controlling software piece. And one of those such systems is called SCADA. It's a type of ICS system, supervisory control and data acquisition system. And it actually gathers data from multiple implementations of all these different ICS systems. Some of them you can send down programming updates. Some of them you can't. They don't have the onboard capacity for doing that kind of networking. And many of them as well, they don't have the onboard capacity of decrypting and encrypting data. So sometimes we have to wrap security around those things under these things called hardware security modules, HSMs. And sometimes we're going to be doing programming. You have to do it on site on each individual. Some of them are called programmable logic controllers, PLCs. And some of them are, they have what's called HMI, human machine interface. But you got to go down and physically flip switches and stuff to change the programming on these things just because of the nature of the beast. And like I say, some of them can do networking, but it can only send short bursts and receive short burst data. It can't encrypt it. So you wrap it with those hardware security modules there to encrypt the data. Because each and every one of those spots there is a potential attack point for a ne'er-do-well jump into that network. See? So that is some of the embedded type of systems we see. We see these things are spread out in just about every environment you can imagine. We see them in agriculture, farming, the medical community, logistics control, communication, transportation networks, and so on. Many of those things are using now sort of repurpose some of the older cellular technologies, the second and the third generation of cellular for communications. So low-level communications capabilities there. So there's a lot of human-machine interface going on these things now. We also see these things, these Internet of Things things. Told you guys earlier about the smart systems we have in our homes. Alexa, turn the lights on. Alexa, turn the thermostat up. That kind of thing, or Siri, and I hope I didn't trigger any of you guys' Alexa devices there. That oftentimes happen when I say that. I've done that before, and I've heard in the background somebody's, a microphone was on, and Alexa says, "I'm sorry, I don't understand your," that kind of thing. So but these semi-smart devices, and I'm talking about everything you can imagine. Um, Smart microwave ovens, smart security systems. I installed the wife a smart thermostat control here, voice control thermostat, and the video doorbell and the security system and all that stuff. So those are some of the things that we are beginning to see now incorporated, not only in enterprise networks, but our residential, our home networks as well. And all of the same concerns we have to manage and monitor there as well on those network connections. Now, when troubleshooting networks in general, the same process goes along with the troubleshooting methodology. Identify the problem, establish a theory as to what you think is causing the problem, and networking is a little bit different. Network host machines. Don't forget about the different tools that I told you guys about earlier, the loop back plug for testing network, on switches and on routers and on individual host machines. You want to make certain that communication ports are open, and sometimes they'll do this thing called port flapping. The ports, for whatever reason, sometimes malware, the ports are turned on and then off, that kind of thing. If you can use individual commands, for instance, to troubleshoot end-to-end connectivity, all the better. And I'm talking about commands like your ping command on your command line interface, your trace route commands to trace a connection from one host machine to another host machine. You want to try to use different tools that we looked at earlier for looking for any kind of interference, radio frequency or electromagnetic interference. You want to make certain that I was telling you guys earlier, if you go out into the field, you need to make absolutely certain that you have two known working copies of any and every cable that you may need to test out there. You need to have all of your testing equipment, your port equipment, your RJ45 line connector equipment, your digital and analog VU meter. You need to have all of that stuff available. You need to understand how to tap into that mirror port that I was talking about on switches and utilize tools such as Wireshark in order to capture traffic and analyze that traffic. Now, most of the stuff I'm talking about here is more of a network engineer's perspective, but told you guys before, you may very well be in charge of some of that stuff as an A+ technician. It is all according to the company that you end up working with or for. Okay? A lot of the times, network issues, what seem to be network issues anyway, can be isolated down to a singular host machine. Okay? For instance, think about it this way. Somebody calls you up and they say, I'm trying to print this document out on this printer here. It's a network printer, but it's not printing my print job. Okay, well, you see if you can print to that printer. If it's just isolated to that one machine, great. You got a problem with their machine, not the entire network. So that's part of the whole troubleshooting process, trying to isolate where the problem actually exists and determining the overall scope of the problem. Is it a systematic thing? Everybody's having the same problem, or is it just an individual having that singular problem? And I was telling you guys yesterday, I'll tell you again, if you can reproduce the problem, if you can reproduce it, you're way down the road of being able to start keying in on what is causing it and thus coming up with a fix for it. Same thing with wireless type of issues. Check the strength of the wireless signal with your Wi-Fi analyzer tool that I gave you the link to before. See if you can identify where any type of interference may be coming from. And boy, some of the craziest places that generate interference in Wi-Fi you could ever imagine. Overhead fluorescent lights. And it's not the light itself. In the old fluorescent lights, they had the little silver starter solenoid that actually charged the gas inside the fluorescent light bulb. That solenoid is what causes the radio frequency interference that oftentimes interfere with Wi-Fi signal. Microwave ovens. Microwave ovens emit radio frequencies that could very well impact Wi-Fi signals. Okay. Another thing that a lot of people just simply don't think about in the Wi-Fi world, the power plant in this little beast right here and the power plant in a tablet or a laptop device is the battery. If you got weak battery here, you're going to have weak networking signal here. And people just don't think along those lines, you know. Or if I've got this and I'm in the basement of a building and I can't get outside as far as Wi-Fi signaling because the Wi-Fi adapter's on the third floor, those are the kind of things that we need to look at. Don't discount anything. Don't take anything for granted. Okay. And ask the questions that may seem like very, very low level stuff, but understand the majority of the people you're going to be supporting out in the field are not technically savvy. They don't understand these simple things. Okay. So low signal strength is low connectivity. Okay. Voice over IP issues. I'll give you an example of this. We have this thing called latency and jitter. When I first when the wife and I were a young married couple, I did a lot of traveling, and right after we purchased our first cordless digital telephone, well, I was doing quite a bit of work out in Jackson, Mississippi, and you got to understand, my lovely wife is Southern Belle. I know I've got a Southern accent, nothing like the lovely Mrs. Helms. So I picked up the phone out there in the hotel room. She was going, "Well, hey, how you doing out there in Jackson, Mississippi?" And it was digital phone. And it was because, you know, I was telling you guys earlier, you tend to think that that telephone call is just one long stream. Well, it's not. It is broken up into digital packets and frames. Sometimes those frames go a different direction. So there's this thing that's latency between each individual data frame, and that it's just a measured amount of time from the time you send it to the time you receive it. What you want to make certain is that latency is consistent among all the frames. What was happening in that situation, the latency between frames 1 and 2 may have been 300 milliseconds, but the latency between frames 5 and 6 was 3,000 milliseconds. So thus the jitter, the latency there. So you have inside of the systems the capability of adjusting, and they call it class of service, quality of service, where you can configure that latency, that variance, so it is consistent across the board. Okay? So if you run into those kind of things, that's what you want to look for, is that quality and class of service or a configuration there to measure out that kind of stuff. Once you figure out what the issue is in the network itself, then again, you begin to you put your go forward plan in place. What are you going to do to actually mitigate the problem? All right, somebody tell me right quick again. If I look at a computer's configuration and it tells me that their IP address is 169.254.6.8, what does that tell me? Anybody jump in? Their IP address. Go ahead, Ryan. I see your mic went hot.
I don't remember what it's called. It starts with the A, but it was the automated IP that Windows gives out. It didn't get a
Yeah, a PIPA, a
DHCP.
PIPA.
Yeah.
Yeah, automatic private IP address. Now, why do I get an APIPA address?
Issues with the DHCP
Yeah, I
server.
can't make contact with DHCP server, and it could be a server problem. It could be a link between the switch I'm talking to and the server. The server may be being rebooted for whatever the reason. My computer cannot contact that DHCP server to get my IP address. Okay. And I would use, in order to check that IP address, the IP config command. Now, I'll be going over some system commands as the week goes along here, and I'll give you guys a listing of the most common commands that we use in the environment. So, and that again is something I would highly recommend you guys use flashcards to, if you don't already know them, to memorize those things. Okay. So those are the kind of things that we troubleshoot when we have, you know, limited and no connectivity. Okay. What network host am I talking about? What is my IP configuration? Do I have an APIPA address? Am I locally connected? Can I talk with people in my same network but not outside? Those are the things that I want to try to troubleshoot and try to figure out. Looking at system logs, I can pick up lots of information by just reviewing the system log, and it may very well help me get pointed in the right direction as far as solving the issue. First, I got to identify it. Then I have to test my theory to see if it is indeed causing the problem, and if that is the case, I need to put in place to go forward with it. If I have the authority to make the call to go ahead and go forward, I do that. Then I verify for myself that the system is working properly. And then I have the user verify for me that the system is working properly. And I document everything all along the way every time. And I always look for those teaching moments as well. Okay. All right, quickly, let's you guys jump over here and take a peek at your lesson quizzes. I want you to go over lesson 6 practice quiz here. Do that guy, post that score, and then I want you to go back and repeat lesson number 5 quiz. Okay. Then I've got one more performance-based question I'm going to step you guys through. Then I'll assign your homework and we'll call it a day. So do this quiz right here. Post those scores. Then I want you to go back and repeat lesson quiz number 5. Post those scores. Only 25 questions total here, so it shouldn't take you guys too long at all. Okay, and I'm not even going to run a timer. I'll just be looking for your quiz scores to be posted here. And then we're going to jump in real quick and do a quick performance-based question. And then I'll have you guys homework emailed to you shortly after that. Okay. You guys need a quick break, or is everybody good to keep going until we finish? All right, let's keep on into it then. You guys go ahead and jump on that quiz. I'm going to bring up your PBQ and have that ready for you as soon as the quiz scores are posted there. Now, you folks that have joined us on the on YouTube, I'm going to go ahead and shut down the YouTube feed now. Thank you all for joining us, and hope to see you in class sometime really soon.